All right. So the last time we saw a bunch of examples how we can restrict kind of certain existence of certain maps with restricted rank. And I want to mention the last one. I will not have time to give the full proof, though it's nice. It's the following statement. So it's, again, somehow, it's not a degree, but okay, let's see. So assume we have a map that goes from the sphere to this to just some Euclidean space. So it doesn't go into the sphere, but it's a homeomorphism. Right? Homeomorphism means homeomorphism onto its target. Right? So think about the parametrization of the Koch curve or something crazier, right? That could be f of S1. Okay? Then, and let it be smooth. Sobolev is also fine. There exists no f in W1n from the full ball into Rn such that the rank of df is at most n minus 1. And of course, it extends f. So, and f on the boundary is little f on the sphere. Okay? So we lost somehow. It looks very similar to a degree 1 map, right? So if you have a homeomorphism and the target happens to be the S1, homeomorphism would mean it's degree 1, right? We kind of dropped that notion. We just map into like some random Euclidean space. Of course, the application was the Heisenberg group. The boundary map is a homomorphism. There's no way to find that the interior map is restricted to the rank at most n minus 1. Okay? And this is, say this, right? So this is Eylash, our student, Jake Mirror, myself, some years ago. And the proof is very, I mean, it's very much inspired from what we did before, but the actual proof then goes through a lemma that we're kind of proud of because we had to translate essentially basic theory from algebraic topology. So the lemma that makes this possible is something which makes everything look like a degree. And the statement is little f as before, then, okay, we don't have a nice target, so we cannot talk really about the volume form. If it was this picture, you would just kind of make it nicer by actually mollifying it or something, but we have an abstract object. But still, we find something, we don't care that it's a volume form, right? We just find some form. So there exists a form, omega, it's smooth. It's n minus 1 form, such that, well, one thing is that it's a closed form. I mean, the volume form is closed on the object itself. That's the point of the volume form. The way we see this here is that d omega has compact support, maybe this has compact support as well, on Rn without the image of the sphere. This is very important, as we will see. So where this f lives, closed, and in the small neighborhood, think about the projection back into the sphere, this form is closed. All right, this is 0 close to this. That's what this says. All right, and such that this number, well, it could be 1, but it doesn't really matter, is not 0. So whenever you have a homeomorphism, you find an omega, very nice object, that vanishes close, it's close to the image, and this kind of degree type formula is not 0. Okay? Again, if f is just mapping into Sn-1, you would just plug in here the volume form. Now, this guy, to construct it, it's a bit long and I have to skip it. It is in my notes, and it's kind of funny because it is in every algebraic topology book somewhere in the first chapter, right? It's a statement that if you look at the Euclidean space without something which is homeomorphic to a sphere, then you can compute certain homology groups. I don't even know if you write this up or down because I screw this up all the time. So certain homology groups, maybe I'll make a question mark, are non-trivial. Right? This is like a statement you prove at the beginning, essentially to introduce the Meyer-Vittori sequence, I guess. So what we did to prove this is we tried to understand this, tried a little bit more, right, and translated this to analysis. But it's essentially copying that proof, right? That some certain homology groups are non-trivial if you take the space and remove something which is a sphere topologically. All right, that's how much I want to say. I wrote the proof down. Again, every step is just, I put, the algebraic topology on one side and the analysis on the other, and I just followed. And I followed the Meyer-Vittori sequence. And it's an induction on dimension. It's kind of a cute argument. Once we have this such a result, right, we're done. We know how to do it. It's just Stokes' theorem now. I squeeze in the proof here, so you all know how to do it, right? Assume this f exists, then f star omega, which is not 0, is the same as f star d omega on the ball, but this is 0 if the rank condition is 0, so, well, contradiction. Okay, that's the proof. Okay. Now you can think, okay, so we can do this. Very nice, very nice. And this is kind of the rest of my lectures. What can we do if we kind of lower this, right? Is this sharp in the Sobolev class? And the first thing I want to talk about is, yes, this is super sharp. There's no way to improve it. And I don't know who proved these things first. I kind of right now, no, I have to find. So I mentioned two people or two groups. Henschel, right? This is the Czech Republic groups, let's say, and Faraco, Mora Corral. That's one person, right? This is. And Oliver. And okay, Henschel doesn't really prove that statement. Faraco proves a stronger statement. So this is kind of the Czech group that likes to work with Cantor sets and explicit mappings. This is the convex integration group. Okay? And so here's the statement. For any alpha less than 1, there exists a C alpha map capital F going from the ball into your Euclidean space, favorite Euclidean space, with bunch of properties, determinant df equals 0. Okay, here we may be a little bit concerned what that means, because I just said C alpha. Well, the map is C alpha and W11. And the gradient, I write this here, the gradient of f is not in Ln, because in Ln it cannot be. It's in weak Ln. We are almost in W1n. The rank, so the rank of df is less or equal than n-1 because this vanishes. And at the boundary, we are the identity, which is, of course, a very smooth homomorphism. Okay? So once you move here, and this is C alpha, for any alpha, you have to fix the alpha first, but maybe you can also boost this. You fix C alpha, you are in W11, and then the gradient is in weak Ln. Okay, so in any W1P, P less than N in particular. You can even, and this is what they show, right, this is even a homeomorphism. It's by C alpha. Right, so it's a very, very good map. Nevertheless, the determinant, the rank is 0, the determinant vanishes. The rank is less than n-1. And you see, this kind of suggests that this is extremely wrong once we wiggle anything, right? We had the sharp case. So what I want to do the remaining part of my lectures is first show you some sort of a proof of that statement in this convex integration direction. Second, show you that we still can do more because we have to just understand what this condition actually tells us. Okay, so there are two things. We want to kind of discuss and better understand what this means in this case. It looks like the same, but this is way worse than this. We'll talk about that. But first I want to actually prove this. Now, it takes too long to actually prove it, so I thought I'd prove it in 1D. Okay? So n equals 1. Because then it's kind of easy and you will see that you kind of know the proof. And then I want to give you a ridiculous proof. But that proof extends to this if one works. All right, what is the statement when little n is equal to 1? Well, Sn minus 1 is S0, yeah? It's false for any C alpha. You said C0, so we are Hölder continuous for any alpha less than 1. Right, so we are almost Lipschitz. Again, it cannot hold for Lipschitz. But arbitrarily close to Lipschitz, any fractional Sobolev space you want, arbitrarily close to W1n. Okay? So what is the statement in 1D? Let's make this smaller. Let's make n equals 1. Let's make this also 1. So we are looking at f going from, well, S0 is plus and minus 1. So let's normalize this. F goes from, 0 and 1 into something, and it's a homeomorphism. That just means it has two different values. Right? So let's say f of 0 is 0, f of 1 is 1. Right? To some translations, that's the situation. So what do we want to prove? We want to prove there exists an f in C0 alpha for any alpha less than 1 from 0, 1 into R, f of 0 equals 0, f of 1 equals 1, and, okay, now we're in 0 dimensions, the derivative should be 0, right? F prime equals 0, almost everywhere. And, okay, on the boundary we have this, we have this. Now, gradient f in weak L1, I don't want even to define, that's not a Sobolev space, right? It's like a non-good space. So what we're going to show is f is in BV. And I assume you know that map, right? That's this Cantor staircase, right? How do we prove the Cantor staircase exists? Well, we look at a bunch of Cantor sets and let the function like move only on the Cantor set, everywhere else it's 0. That's kind of the proof of this if you follow that group. Okay? I want to discuss this. So I want to prove that statement, or kind of sketch the proof, how you will prove that statement with kind of convex integration methods. And, you know, with a substantial amount of work, you can do this in higher dimensions as well. That's kind of the gist. I dropped this notion that this is a homeomorphism, okay, because that's complicated. Not even sure it's true. Okay, statement clear? We all see this is the Cantor step function, the Cantor staircase. All right. So how do we prove this statement here? Well, we start with a lemma. Lemma will be. Let me want to keep this. Okay, I go to the right. So lemma. This is the basic construction in 1D, and it's kind of the basic construction in any dimension for these laminates that you can use in convex integration. All right, so here it's very simple, but it's really the main idea. It somehow goes back to Nash, I guess. So assume we have three numbers. Let's call them A, B, and C. Three real numbers. I don't want, for triviality reasons, B and C to be the same. Okay, that would be pathological case. We have a convex guy, and we want that A equals lambda B plus 1 minus lambda C. So A is in the convex hull of A and B. B and C. All right. Take an interval, which is AB, finite. Again, everything can be extended. Fix an epsilon greater than 0 that we talk at the end. D in R. And what do we want to do? We want to write, essentially, we want to find an F going from 0, 1 into R, sorry, from AB, with a bunch of properties. The first property is, globally, or at the boundary, F looks like AX plus D. So F equals AX plus D on the boundary of AB. Okay? Let me draw a picture. So this is my AX plus D. Right? So that's A and that's B. We have some linear map. Okay, and we want to find a function that this is at the boundary. Okay, I want this to be Lipschitz. And actually I want this to be piecewise affine. Right? And actually what we will have is we want a finite union of pairwise disjoint open sets where this function is just affine. And then what is left to cover all of AB has to be finitely many points. Okay? So, all of this is so far trivial. Now, the main point is I can make sure that the slope of this function, where it is defined, is either B or C. Okay? F prime equals B, or F prime equals C almost everywhere in AB. Okay? Good. How do we do this? If we stop here, this is a sawtooth, right? If the slope here is between a steeper slope and a less steep slope, then we just have F somehow something of this type. Right? One is steeper, maybe that's a C, and then one is not so steep, that's B. Okay? So whenever we have a function that is AX plus D, we can replace it with two other guys, and it has a steeper slope, less steeper slope. This is this condition. Okay? We can also compute, if we look at this, on what size of set we see the slope C, and what size of the set we see the slope B. Right? So I write this here. If I look at F prime equals A equals C, and I measure this, this will give me, let's do B first. This will give me lambda times B minus A, and F prime equals C will be the rest, 1 minus lambda B minus A. Okay? That's the basic idea of convex integration. All right? Maybe we are not so happy with this. Somehow I like to think of this. We want to find a function, F, this one, but it should be very close to the original. Not only at the boundary equal, I want it to be very, very close. So that's the epsilon. I want to make sure that f minus ax plus d in the L infinity norm is less than epsilon. Okay, the picture doesn't do this. What do I have to do to the picture that this happens? I have to wiggle a bit more, right? I have to do something like, right? And then I have this function. And again, it's a function that is essentially outside of finitely many points. It is just differentiable in the classical sense. It's actually affine, right? On each of these intervals, these are open intervals where it's affine, and the derivative either C, like here, or B, like there. So they're countably, I mean, they're finitely many intervals in higher dimensions, they're countably many. Okay? Do we all agree on this lemma? Right? So this is the good old sawtooth. All right. So we can approximate ax plus d with functions which look like they either have the slope b or the slope c. And the idea here, or generally in this laminate kind of situation, is wiggle enough. We want to solve this equation. We don't have it in the beginning, so we add wiggles until we have it. We do this kind of in a structured way. And you could see that there is a Cantor set appearing there, but in higher dimensions, it's maybe more difficult. All right. So that's the basic construction. And now we just iterate. And the iteration is an induction. So we start now with the map f minus 1. That's the first attempt. It's completely wrong. It is x. It's just the identity. Good thing is at 0 it's 0, at 1 it's 1. Okay? And then, for technical reasons, the first iteration is still x. Okay? And now we start to wiggle. So here's the lemma. Basic iteration. So k equals 0, 1, 2, and so on. There exists an fk, goes from 0 to 1 into R. Lipschitz, piecewise affine. All right. And fk of 0 is 0, fk of 1 is 1. Okay, so that's always, we always try to improve our x here. And we have the following situations, okay? I write, what we know is the set where f prime is equal, fk prime is equal to 0 is at least 1 minus 1 over k. So we see as k improves, right? And for k equals 0, there's no condition. For k equals 1, it's true. The set where fk prime is equal to 0 gets better and better. Then we have that fk prime equals 0. This is a bunch of intervals, right? These are open disjoint intervals from this piecewise affine thing, and they only get more and more. So the piecewise affine situations where the derivative was 0, we don't wiggle anymore. So what we have is this kind of increasing situation when the previous guy had its derivative to be 0. Those intervals we don't touch, and so we stay 0. Okay? This increasingness is important. Then, that's where this epsilon comes in. These increased steps we can make arbitrarily close to each other. Fk minus fk minus 1 in the Hyder norm, this is where alpha needs to be fixed, is less than something very small, and we want something that we can sum up, so we take 2 to the minus k. Okay? Observe, there we have the L infinity norm, here we have the C alpha norm, right? And overall, fk prime is at most k. So the derivative will get very large. As k goes to infinity, it will happen only at very fewer and fewer points, because this here becomes larger and larger. Okay? I think that is, so this is almost everywhere, again, in the sense of these fine sets where we are fine. Okay? I hope we can agree this is satisfied for these initial guys, right? It starts with a 0, this is nothing, right? This is an empty condition. There's nothing of this sort, there's nothing of this sort, there's nothing of that sort. Okay? I mean, fk prime is at most 1. All right, so how do we prove it? Induction, obviously. And so we just have to go from fk to fk plus 1. Okay? So, proof. Assume fk is constructed. Construct fk plus 1. All right. So now, fk we know it's piecewise affine, and so we can decompose 0, 1 into a bunch of intervals where fk prime is 0, maybe none, and where we're not 0. So we write 0, 1 is the union k equals 1 to some n, right, finitely many, of ik's. Then we have the union j equals 1 to m. This is some jk's, and then we have some finitely many points, right? And this here are open intervals. So this is open disjoint intervals, and we assume always that we have chosen them so that we are piecewise affine, that we are fine on them. Ik is the one where f prime of k is 0. We have no interest to change them there. Why would we? Right? We just focus on one of those. Those we keep. Right? And so this is fk prime is not 0. Those are points. Finitely many. Again, right? And if you do the same in higher dimension, you get more, but it's always countable. So these are lower dimension. All right. So what do? We want to construct the fk plus 1. What we need to improve is this, right? Under all these constraints, right? Somehow we want to improve, this we want to kind of survive. Okay, so we take these, everything here is disjoint, right? So we take one of those jk's, call it j. J, right? So fix some j. What do we know on j? We are affine, because we're piecewise affine. On j we are affine. So fk on j, which is somewhere, looks just some slope. So this is somehow fk. We want it to be 0 more. So what do? Well, we know that fk prime is equal to some a. Okay? All right, so that's the a here. Right? This is a guy we don't like. What do we want? We want a 0. Well, a is either larger or less. I mean, it will always be larger in this case. So a is certainly a convex combination of 0 and something larger. Right? So let's assume, without loss of generality, a is greater than 0. It's not equal to 0. If it's less than 0, we do exactly the same thing with negative signs. And then here, a is lambda times 0 plus 1 minus lambda times, and I just go to k plus 1. Go to a plus 1, but why bother? Right? That's certainly possible because the derivative of f, by assumption, is at most k. We just push it one step further. Okay, so we write a, which is somewhere between 0 and k, as convex combination of 0 and k plus 1. Okay, and computation, we can compute what lambda is, right? That's very easy. It's also easy to screw up. And we just pretend, I mean, we don't really care what lambda is, we care about a bound. And so we pretend that this is k, and then you have subtract. And let me see. So I got that lambda, and I hope it's correct because all the numerology depends on it, that lambda will be at least 1 over k plus 1. Again, if that's wrong, you have to redo everything and put some other numbers somewhere else. Okay? So a is less than k, so we know that we can kind of interpolate between 0 and k plus 1, and we know that this lambda is not very small. We know it's at least 1 over k plus 1. All right, so convex combination, we have a linear function. So, fine linear, we have this wiggle lemma. Right? We have the convex combination, we fix an epsilon we still have to discuss. So let it be an epsilon to be decided later. We have this d, that's just the linear function. We find a function that at the boundary coincides. So we don't mess with continuity. Right? So at the boundary it coincides. Let's write this down. There exists an f going from J closure into R. On the boundary of this J, we are the ode Fk. Right? Because that was continuous, so this is the continuous, that's all defined. All right? And what else do we know? We have this epsilon that we have to talk about, and we have that the derivative is either 0, it's good, and we know how often, and the derivative is not 0, well, on the complement. All right, okay, so we have this, and we know that the derivative f prime equals 0, in this is a subset of J, right, is at least 1 over k plus 1, the size of J. Right? Okay. And we know that f minus fk, maybe I put this here because I'm running out of space, f minus fk, L infinity is less than epsilon on all of J. Okay? Good. What do we do now? Okay, now we replace fk on the set J by f. We stay continuous. So I pretend now there's only one J. We do this for every J. Right? Continuity gets preserved. So fk plus 1 is fk, not in J, and it gets this f in J. Okay? This is continuous. That's extremely important. Right? That was the boundary data. Good. So this is a continuous guy. It's still piecewise affine. Right? This f itself is piecewise affine. Right? So now I replace this. It's less piecewise affine. Right? It has more movements, but okay, who cares? So this is continuous. Good. We want a bit more. We said it's Lipschitz. Well, it's actually piecewise affine, so I guess it's Lipschitz in any case. So where is my... Yes, my induction. So fk plus 1 goes from 0, 1 into R. Great. It's Lipschitz because it's piecewise affine. Good. Boundary data didn't get touched. Good. All right, we have to prove this. All right. Well, let's do this. What do we know about fk plus 1 prime? Well, if we are in those sets, we didn't change anything. right? So if I look here, and I look at the size, this is greater or equal than the size fk prime equals 0. There we didn't change anything. Plus the size where f prime is 0. Could be larger if you had forgotten something, but it's this plus this. All right, this is the old guy. So for now we don't touch it. What do we know about this? This here is lambda times j, right? And somewhere I wrote this. It's at least 1 over k plus 1 j. So this is larger or equal 1 over k plus 1 j. We do this on all the j's. The union of the j's has the measure 1 minus that union. That guy, right? So the union of the j's is everything which is not here already. So we get that this whole thing is fk prime equals 0. This is a 1 plus 1 over k plus 1 of 1 minus f, this set. fk prime equals 0. Right, because that was the sum of the j's. All right, now I compute what I have, and if I didn't screw up the numerology, what I get is that these things, because here I know this here, right, this we can add to this, so this is 1 minus 1 over k plus 1 times the old number plus this. And so, again, if I didn't screw up, then this here, see that I wrote this the right way? Yeah, so this would be closer to 1, and it will be 1 minus 1 over k plus 1. Again, I did a bit more careful computations in here, but you know, right, this is algebra. All right, so the set where fk prime is 0 has improved exactly the way we said, like in a controllable way. Good. So we have this, right? We only changed anything where we weren't 0. We still have to talk about this. All right, now what we have from this wiggle lemma is only L infinity, but that's kind of the fun thing. Cannot decide. All right, the j is gone, and I do this here. All right, what do we know about the C alpha norm? Nothing. All right, let's lower our standards. What do we know about the L infinity norm? Well, the L infinity norm, fk minus fk plus 1, L infinity, all right. On most of the sets it's the same, there we don't care, it's 0. And on the sets where it's not the same, well, it's epsilon. By this construction, the epsilon we still can choose. Right, so this is less than epsilon. Right? Okay, but we want C alpha. Good thing is, C alpha is interpolation between Lipschitz and L infinity. Right? What do we know about the Lipschitz norm? Is it small? Absolutely not. It's pretty large. The Lipschitz norm is maybe 2k plus 1. I don't really care to be very sharp. I just want, it's a number which depends on k. Right? Because fk prime and fk plus 1 prime is at most k because of this decomposition. Right? Okay, so what do we have to do? We have the L infinity norm less than epsilon. Epsilon we can choose depending on k. And the Lipschitz norm is 2k plus 1. We interpolate. And so since alpha was fixed from the beginning, we can choose epsilon very small, depending on k, such that fk minus fk plus 1 is less than 2 to the minus k. Right? This is interpolation. You can do it by hand. The C alpha norm is interpolation between L infinity times a very small factor of this. That's why this is true. Okay, kind of jumped over this, but we have everything. Okay? Say again? W1n norm, yeah, we still have to compute it. It will stay finite in this case. So n is 1 for us, right? So in higher dimensions, okay, let me compute it. So this is a very good point, right? Now we want to conclude. That's essentially what we care about. Right? This is this iteration. Now we conclude, but just by taking the limit. Okay? And then we have to look at the norms. And this is something which is a bit more complicated in higher dimensions, some other parts which are a bit more complicated, but this is the outline. You look at those papers. All right. So we have this lemma by induction. So we have a sequence Fk. The neighbors are very close, so we can sum this up. So we have a Cauchy sequence in C alpha. Right? So Fk is Cauchy in C alpha, hooray. So Fk converges to some F in C alpha. Fantastic. Asilascally. All right. That we have. So now, let's just go through the things that we want. Fk was 0 and 1 at the boundary, so F will survive in this thing. So F of 0, 0, F of 1 is 1. F is in C alpha by convergence. Yeah, now comes kind of the part where we have to be a bit careful. Maybe we first do the W11 question. What do we know about F prime? Fk prime? Well, Fk prime is 0 here, and that means the norm is not very large. Right? So this here on 0, 1 is simply the integral on Fk prime not 0 of Fk prime. Generally true. Now, how big is this guy? At most k. Right? So this here is k times the area of this. And now where it's equal to 0 is 1 minus 1 over k. So where it's not equal to 0, it's 1 over k. Right? So we have 1 over k. So this doesn't go to 0, but it's bounded. Observe, if you put here a p less than 1, right, then it actually goes to 0. So we have a sequence which converges in W1p for p less than 1, which is not a very useful notion. Okay? But that's what happens in higher dimensions, right? You kind of stay below the exponent, you go to 0. You are at the exponent, you don't. But you stay bounded, so we have now a sequence in W11 uniformly bounded. Does it converge in W11? Nah, not reflexive, but they exist, this convergent subsequence in BV. Right, so this shows that F is actually also in BV, right? Because we are bounded. Good. We didn't care about either of this, but let's go back to what we want to show. This. The derivative doesn't converge pointwise, right? There's no such thing, right? We have very weak derivatives. The derivative doesn't exist in distributional sense. It's not a function, right? But we have this, right? So we have this monotonicity of where we already attain what we want to attain, derivative being 0. So by monotonicity, F prime is equal to 0, right? This set is the subset of Fk equal to 0. A little bit needed there. Okay? Why? Because it's piecewise affine, right? On those sets, we didn't change it. It's not like convergence argument, right? It's saying, look at the intervals where this is actually 0, Fk doesn't change at all there. Right? And that's why this is true. It's not just monotonicity of sets. It's a bit more care. Well, this means this is less than this, and this here goes to 1. as k goes to infinity, which means that this set must have size 1. And it's classically differentiable on a set on a union of bunch of intervals that have full measure. The complement is a Cantor set, most likely, right? All right, that proved this statement. Now, in higher dimensions, a bit of warning, right? Rank being less than n minus 1 doesn't say that the derivative is 0. Those are two very different notions, right? In 1D, that's the same. In higher dimensions, you can do this trick here for determinant not 0, and equal to 0, and you can do this estimate. That doesn't control the full gradient. So that's an extra step you have to do, right? So you have to be a bit more careful. All right, that's the proof. We've spent a lot of time on proving the Cantor step function. But yeah. Sorry, yes. Greater or equal because it got larger and larger. Thanks, yeah. Right, so we don't change it where we used to be and then already 0 and then we added more and more, yes. Okay, so again, this is not just, this written as that doesn't imply this, right? These are union of open intervals where we don't change the function and thus it converges. Okay, and that gets a bit more complicated in higher dimensions, if we are honest. All right, any questions? Yes. But we are a subset of 0, 1. Yes. So we have proven that the set where the derivative, since it's the union of open intervals, actually is differentiable, holds almost everywhere. Okay? Any other question? Yeah. Yeah, still stay away from the boundary. So you're right? In 2 dimensions, you have to be careful how you wiggle, right? Because you kind of wiggle now in 2-dimensional sets, and those sets are like polytopes. Yeah, but you can cover every set with like copies of same size polytopes densely. This is kind of Vitali, right? So this is what you do. That's why you get countable and everything. So essentially in 2D, you do such wiggles, and somehow how you do the wiggles defines the set on which you're going to do them. Let me pretend it's a parallelogram, right? So on that set, you do your wiggle, and then that set you can rescale, copy and paste all over, disjoint of your open set where you want to do something. Right? Now, there is an issue there. We can talk after class as well, right? There's an issue there that in order to get to the polytope, you have to regularize, and so you have a set where nothing happens, or where something random happens. So you have an error set, it's not as precise as here. 1D is easier. Okay, so there is a bit more of covering, and there's like you have to redo the argument all the time, because you will miss a set in order to be actually in the polytope, in order to preserve the boundary data. Okay, so I'm cheating a little bit, right? But I claim that's the basic idea of this whole laminate business by Farako et al. All right, so what have you proven? What's the time? Okay, what have you proven? Let's assume we have proven either this, or if you believe me, we have proven this. Okay, we got some W1 whatever function with the determinant equal to 0 almost everywhere. In 1D, what does this tell us? If the derivative almost everywhere exists and is 0, is that a geometric information? Apparently not, because we can create stupid functions. So what goes wrong in 1D already with this sort of example? Something we usually associate with the derivative, but which is just wrong here. Well, the fundamental theorem is wrong, right? Being almost everywhere differentiable doesn't tell us anything, right? That's not a really proper notion of derivatives, right? So this derivative is not distributional, right? Simplest example would be take the Heaviside function, okay? Then h prime equals 0 in that same sense almost everywhere. But the function is not constant, which tells us derivative almost everywhere equals 0 is kind of a rubbish notion. Okay? And what we should look at is distributional derivative equals 0. That's a geometric information. Do we have any chance of getting the distributional derivative here equal to 0? Well, no. If the distributional derivative is equal to 0, we are in W11. Actually, we are in W1 infinity then. We're Lipschitz. There is no way that there's a Lipschitz function going from 0 to 1 and the derivative is almost everywhere 0 by the fundamental theorem of calculus. F of 1 minus f of 0, right, would be the integral of the derivative. This is true for distributional derivatives if they are functions, right? This here is just not true. This is essentially a counterexample against the fundamental theorem of calculus, very complicated one. Okay, so there is no way that we can get this example with distributional derivative equals 0. And if we are not actually in L1, in W11, distributional derivative equals 0 and just derivative being 0 almost everywhere are two different notions, very different. Clear? Right? So if we were in W11, that's the same as saying the derivative is 0 in distributional sense. We are not in W11, so this is a completely different notion. And the other notion, distributional derivative equals 0, cannot happen. So we have some rigidity if we go to distribution notion. So what does it tell us here? Here we found something, right? Cool things, where the determinant doesn't make sense distributionally. Or it does make sense, but the distributional determinant, or the distributional Jacobian, is not the same as the almost everywhere Jacobian. This notion that this here holds almost everywhere is the same way as over there, meaningless. And that's why we can construct this example. Okay? So the question that we could ask is, going back here, can we replace this with fraction Sobolev space? I will write C alpha because it's shorter. Can we replace this with CS? Certainly we cannot have this like pointwise almost everywhere. Faraco et al. Example or Henschel. But this here we want to discuss in distributional sense. Then we have a chance, right? And this is a more geometric question. Now we have to discuss what the distributional sense is, right? But essentially, like in 1D, when we just say f prime equals 0, distributional sense versus pointwise, and the change happens at W1n, where n equals 1, we have to discuss the same thing here, and then we are maybe back on our feet to kind of extend this, well, this theorem. Okay? So, I want to keep this. Let's forget about these negative counterexamples, try to do something positive, and let's talk about the distributional derivative. Okay? Unless there are any questions. All right. Distributional Jacobian. All right, what's the distributional Jacobian? Let's go back to our first time we talked about Sobolev spaces, right? What is the distributional derivative? There's a bunch of different definitions that happen to be all equivalent. One way to think about this, and for many applications I think this is the most intuitive one, is density. Let everything be smooth, take the norm and close things. Right? So how could we think of the distributional derivative in this sense? Let f be in LP, then d alpha f equals g in distributional sense. And let's now assume this is some LP as well, right? So we talk about W1P. If and only if, for any smooth approximation, I don't write domains, who cares, right? For now, it's just bit handwave. F epsilon smoothly, doesn't even need to be smoothly, approximates F in LP, or now let it be strongly, right? We have that d alpha F epsilon times phi converges to G times phi. Right? That's kind of a notion of partial derivative in the sense of distributions. We don't like to use this, right? Because it gets very long if you were to use it. But it is one, right? It's the one. And you see, okay, the convergence is an LP, and L1 log would be enough, right? We do integration by parts, pass the limit, revert it, and we have the weak derivative. So that is a way we can approximate, or we can talk about distributional derivative of f just by smooth functions. So the idea for the Jacobian is exactly the same. Just take smooth approximations and take the limit and see what happens. So, same idea. We want to say that the determinant of df applied to the test function phi is simply the limit, as epsilon goes to 0, of integral determinant df phi times phi. And this is any smooth approximation. Now, like for Sobolev spaces, there's no reason this has to converge, right? And generally it won't. Right? I mean, that limit may not make any sense, right? But maybe surprisingly, we can show that this makes sense if we're in the right Sobolev space or Hyder space. Below one derivative. We don't need one full derivative for this thing. And this is essentially a version of this Coif-Malliot-Meyer-Semmes compensation effects that Yannick mentioned, the diff-Kerr lemma and all of this again, right? So the fact that this makes sense for a certain class of Hyder spaces is essentially interpolation of Coif-Malliot-Meyer-Semmes. And it's Oder. Funny enough, but okay. Right, in particular, the example that we have seen here before by Henschel / Faraco et al. Essentially shows examples where pointwise and distribution Jacobian are just completely different. Right? And once we have defined this, right, maybe I mentioned this once, right, this means we can talk about rank. We just say the determinant or subdeterminants vanish. Right? The rank being less or equal than a number means that the determinants of that size all vanish. If you can write the determinants, we're done. All right. So here is a cute, it's one of my favorite kind of arguments, and I will show two arguments. Okay, opposition, only one. We take a test function CC infinity of omega. And now I write for CS, and this is the funny numerology. So I wrote in the notes, I write the Sobolev versions, okay? I now talk about CS, again, saves me a bit of writing space. So assume we are in CS where S is larger than n minus 1 over n. You can also talk about the limiting case, but you have to be more careful. I don't want to do this. And the statement is the distributional determinant that are defined here is well defined, no matter what f is, as long as it's in the right space. The distributional determinant is well defined for f in CS. Omega and omega is n-dimensional. Okay? How do you prove something like this? Well, it's simply an estimate. The estimate is, we just want to show this converges to a number, and that should be independent of these f epsilons, right? And so we need to look at differences. f1 minus the integral f2. Okay, these are all smooth functions. Everything has to be done on smooth functions. This omega is less or equal than, it's a multilinear operation, so we get one difference and the rest are, so this is f1 minus f2, that's the difference guy. This is 1, then this is n cross n, so there are n minus 1 more terms. So I write f1 plus f2 cs to the n minus 1, n minus 1. And then phi is cc infinity, so we do the best we can. We take phi in the Lipschitz norm. Okay? That's the statement we have to prove. Once we can prove this statement, this sort of inequality, when we plug in f epsilon and f epsilon prime, right, so two f epsilons of the same approximation, we see that if they go to 0 in this norm, right, then this stays bounded, phi is fixed, we converge. Okay? There's a little bit of a hand-wavy thing that, of course, functions in CS we cannot approximate with smooth functions in CS, but we have S strictly larger than n minus 1, so this will not be a problem. Okay, there's a little bit of technicality. All right, so we have to prove that statement. Clear? And actually, we don't even have to prove that statement because this is a multilinear function, right? You can just, this is like a bunch of multilinear guys. So what do we have to prove? Namely, all we have to prove is, forget about this, just have df phi is less or equal than f cs to the power n times phi Lipschitz. Okay? How do we prove this? Now there are two ways, and both two ways that I know. Both I think are very interesting, and for different reasons. They're probably both equivalent. So one is messy, and to make it really complete, you probably need Trivial-Sorkin spaces and paraproducts. So it's really messy, but I claim it's more intuitive than the other one, which is beautiful and needs one line. Okay, so let's do the messy one first. And I found this in like a version of this, not for the Jacobian itself, but there's like this paper of somewhere in the 1980s of Tatar. And essentially that's the argument that we're doing here. And it's really nice. Now, I don't want to go through little Paley projections. I don't want to do too many convolutions. So I will go to dimension 2. Everything can be extended, but dimension 2 is fun enough. What do we do? Well, Fourier transform. Okay, that's little Paley is always Fourier transform. So we do a Fourier transform. Phi is in CC infinity, omega is some domain, I don't care, it's Rn. R2 in this case. So we want to estimate R2, some weird extension of F, determinant df, maybe we call this df1 df2, right? So we have two entries times phi. Now we do Fourier transform. All right, Plancherel. I will completely screw up the bars. Don't matter at all. So let's ignore that. That's Plancherel. Fourier transform here, it was a product. Okay, phi hat, maybe I call this phi hat of xi, and this is whatever that is of xi. Determinant is multilinear. You can write it as a bunch of products. Products and a Fourier transform convolution. So this here becomes integral R2, now the integral on the phase space again, and it's a convolution of F1. Let me do F and G, okay, then I don't have to write so many indices. F and G. All right, we get F, convolution with xi, so we have xi minus eta, okay, G, eta, and phi hat of xi. Okay, that's the three functions that we will see in the convolution, double integral, d eta, d xi. And now we have to compute the symbols. Well, the symbols just are the symbols of this guy and of this guy. This guy, F, has xi minus eta. The symbol of the derivative is I times xi minus eta times some garbage, right? So I forget about the I because there are two, they go away. So I write just xi minus eta, F hat, and this here will be eta, G hat. And then the determinant, right, again, it's multilinear. You factor it out, do it component-wise, and then compute the product again. So this will be the determinant of xi minus eta and eta. There's some constant here. There's surely some bars that are screwed up. Doesn't matter at all. Okay? So far, nothing happened. All right, 5 minutes, but we can do the main observation. What's the main observation is, hey, there's a determinant. Right? And you can check if there was an absolute value squared or something, it just fails. What is so special about the determinant? Well, we can compute it. What's the simplest possible estimate for this determinant? How does it grow? Xi minus eta times eta. All right. What else? It's a determinant. It has cancellation. Eta and eta are linear dependent. So this determinant is the same as the determinant xi eta. And it's the same as the determinant xi minus eta xi. Because it's a determinant, it has a structure. So I have a bunch of estimates. Those three estimates I have. All right, which one do I want? I want all three, but in a certain weight, right? Well, what do I want? Let's go back. We want to see the Lipschitz norm of phi. So we want to see one full derivative of phi. That's xi to the power 1. And then we want to see as little as possible derivatives of f, right, of each of the entries. So everybody gets the same, right? Each of the f's gets the same. So what do we want? We are happy with the xi, but everybody gets 1/2. So we interpolate these two with power 1/2, and we get that the determinant is actually less or equal than xi, great, that's the derivative of phi, and then only half a derivative of f and half a derivative of g. That's what Tata did, right? All right, 5 minutes, good. What does this tell us here? Well, the determinant grows like these numbers. So let's divide and multiply by these numbers. I multiply with xi. It's kind of the same as the derivative of phi. So what I do is I write here a d phi Fourier transform, and I divide by 1 over xi. It should be xi over mod xi, but who cares? All right, I do the same here. What is this? Xi minus d to the half. It's half a derivative, or a quarter of a Laplacian, right? So I like to write this as d 1/2 of g at eta. And I write here d 1/2 f of psi minus eta, and then the Fourier transforms. This is d phi, and I write eta 1/2 psi minus eta to the 1/2. Okay? Now, what do I know about this expression? It's bounded by 1. Actually, it's not only bounded by 1, but it really, really behaves in frequency space like 1. But to really do this, you need little Paley projections and all this. But let's pretend it's 1, just to see what happens. This is 1-ish. And of course, in Fourier transform, taking estimates is death. But okay, what do we see? Convolution of the half derivative of f with half derivative of g in the Fourier transform, Plancherel inverted. We get the product of this, this, and this. So Plancherel tells us that we have half a derivative of f, half a derivative of g, and one derivative of phi-ish. And now we look what we have here. Holder's inequality. This is less than L2 norm of f in the half derivative, L2 norm of g in the half derivative, L infinity norm of the derivative. So we see here f in h1/2, half a derivative in L2, g in h1/2, half derivative in L2, and phi in Lipschitz. And now we were in n equals 2, and if I didn't mess up, n equals 2 is 2 minus 1 divided by 2 is 1/2. So that essentially proves that. And this S larger, strictly larger, is just needed for embedding theorems and not having to worry about things. Everything can be made precise for equality. So that proves this statement, modulo all the details, which are not few, right? Modulo essentially going through Graphakos and doing all this stuff. But maybe that's a good time to stop. So this is, I claim, a nice way to see what's going on with these determinants, because you can really just estimate the symbols and see how they behave, and then you know what you kind of expect. What I'm going to show tomorrow is the same proof, essentially on 2 lines, way more beautiful. It's due to Brzezinski and Nguyen, but it doesn't really explain that well, in my personal opinion, why this happens. So I always prefer to first compute in the Fourier transform what's going to happen, and then use extension arguments like Brzezinski and Nguyen to actually prove it, because they're more readable. Okay, so I stop here. If there are any questions, let me know. Say again?
Yeah,
a measure definition. You can define the Jacobi determinant, essentially the Jacobian via measure, essentially Rado-Nikodym, right? And you can do this for CS. For example, you could do something like, we know the Hn Hausdorff measure of F, essentially the area formula, right, is the Jacobian of dF. Assume it's 1-to-1. Okay, when we do for Hilda, we could do this for an alpha. The same proof, it's Rado-Nikodym, means that there's some sort of alpha derivative, right, if it's Hilda, that this formula holds, and then you call this a Jacobian. I have no idea if there's any relation between those two notions. I cannot compute this for anything, not even for a Cantor. You wouldn't like to compute this for a fractal. I cannot do anything. So there is a measure theoretic version of defining something like an alpha Jacobian. It's not that one. I believe they're different. But I cannot show anything really, yeah. No, exactly. W11, it's 0. You cannot expect W1n. You get W1n minus epsilon. Yeah, so it's kind of the same, or I like to argue it's the same. The actual geometric space you cannot expect, because the Jacobian tells you something, and this is somehow a result that the Jacobian doesn't tell you anything, right? So this cannot happen in geometric reasonable spaces.